Here there are two circular coils carrying current. It's asked to find net magnetic field at the center of circular coils. The coil is made up of uniform resistance wire. Means equal sections you cut out, the resistance will be same. Half circle, whatever resistance, the next half circle also will be the same resistance. In the first case, the current enter at the left end of the circular coil, divide into two. One part will go through the upper semicircle. The other part will go through the lower semicircle. Since the wire is of uniform resistance, the upper semicircle and lower semicircle both will have equal resistance. So the current will divide equally and pass through the coils. So this current will be I by 2. This current also will be I by 2. We need to know the formula for finding magnetic field due to a circular coil. For a circular coil, magnetic field at the center is mu0 n I by 2a, where n is the number of turns of the coil, 100 turns, 10, 20 turns, whatever given. Here it is just one turn, so n equal to 1. I is the current passing through the coil. A is the radius of the coil. If it's a full circle, this formula is valid. When it's a half circle, the field also becomes half. When it's a quarter circle, it becomes 1 by 4. 3/4, it becomes 3 by 4. The general formula for finding magnetic field due to any arc, 60-degree arc, 30-degree arc, etc., be equal to complete magnetic field is mu0 ni by 2 times of the radius into what angle you need to find out of that 360. Full circle is 360. If it's half, so it will be 180 by 360 will be half, like we got in the last case here, 1 by 2. If it's a 90-degree arc, it will be 90 by 360 will be 1 by 4. So this is the general formula for finding magnetic field due to arc of a circle. Since 360 is in degrees, this theta also must be in degrees. Now, in the first case, if you take the top segment as 1 and the down segment as 2, the magnetic field due to coil 1 equal to mu0 I by 2. The current is I by 2. Number of turns 1, so let's count 1, divided by 2 times of the radius. So assume the radius as A will be 2 times of A, equal to mu0 I by 4 times A. But this is a half circle, so you have to take theta by 360. Theta half circle is 180. 180 by 360. Again, one more 1 by 2 will come. So it will be coming as finally mu0 I by 8A. Magnetic field, electric field, etc. are vector quantities. So you must find always the magnitude along with direction. The rule for finding magnetic field, if the current is anti-clockwise current, the magnetic field is out of the paper. You can use right hand screw rule. or just learn directly anti-clockwise current. The magnetic field is out of the paper, which is taken as K cap. So if the current is clockwise, the field will be in the opposite direction, that is into the paper. For clockwise current, the field is into the paper. So B, whatever value calculate for circle, semicircle, part of a circle, it will be into the screen. So here the segment 1 is carrying current in clockwise direction. So clockwise direction, the field is into the paper. It will be along minus K cap. Now if you repeat the same process for the second part of the coil, coil 2, I mean second half circle, semicircle, current is I by 2, radius is A, it's again half of the circle, everything is same. Only one difference, if the current is clockwise here, the current is anti-clockwise here. That means same magnitude but in the opposite direction. So similarly, you can get B2. So B1, B2 equal to mu 0 I. The same process will apply 8A along K cap. So the net magnetic field at the center, since B1 and B2 are equal and opposite, when you add B1 plus B2, will be equal to 0. Now the second part, what difference it makes if it's a circle with 90-degree arc and 270-degree arc, means 1/4 of a circle and 3/4 of a circle. So here current will not divide equally because the resistances are not equal. So if you want to find out the current through each segment first you have to find the resistance of this segment. So if you mark this as segment 1, segment 2, if entire circle has a resistance of X ohms, R1, resistance of the first segment will be X by 4, where X is the resistance of the entire circle. And R2, the 3/4, will be 3/4 of X. Now you can imagine this wire to be a parallel combination of two segments. You redraw this. These are the two wires carrying the current into the circle and out of the circle. This lower segment you can imagine as a resistance here, and this upper circle, 3/4 of the circle, you can imagine as a second resistor connected between 2 points, R1 and R2. These two are in parallel. In parallel combination, the voltage remains same. So V1 will be equal to V2. So this current, if you take as I1, this current as I2, so V1 equal to V2 can be turned into I1 R1 equal to I2 R2. I1 we don't know, but R1 R2 we have already estimated as X by 4, and I2 with R2 as 3X by 4. So X by 4 get cut. You get I1 current through segment 1 is 3 times of current through segment 2. And the direction is also different. I1 is anti-clockwise, I2 is clockwise. Now you can find magnetic field of 1/4 of the circle. For full circle, it is mu 0, I1, n is 1 by 2 times of the radius. But this is only 90-degree part of the circle. This segment is only 90-degree part, or 1 by 4th of the circle. So the magnetic field will be only 1 by 4th. Since the current is anti-clockwise, the magnetic field will be out of the paper k cap. Now this total field will come as mu 0 I1 by 8a along k cap. Now you want to estimate magnetic field due to the 3/4 of the loop. So that B2, if it's a full circle, means 0, I2, number of turns 1, by 2 times of the radius. But it's only 3 by 4th, 270 degree. 270 by 360 you cut, or 3 by 4th of the circle. The current is clockwise, so the magnetic field is into the paper, minus K. So this value will come as 3 times mu 0 I2 by 8a log minus k cap. This is field 2. Now if we check field 1, we already got current as I1 as 3I2. So if we substitute that here, the value of B1 will come as mu 0, I1 becomes 3I2. So 3I2 by 8a along k cap. So if you check these two fields, both are equal in magnitude but opposite in direction. So the net field at the center, when you add both being equal and opposite, so the net magnetic field becomes 0. So if the circle is uniform, it doesn't matter whether you divide the circle into two equal halves by keeping the current entering and leaving, dividing the circle into 2, or dividing the circle into quarter, 3/4, or 60 degree, the remaining 300 degree. Whatever be it, if it's a uniform circle, if the current is entering through one segment and current is leaving from any other segment of the circle, the net magnetic field at the center will be 0. Because you can see here, the resistance is less, the current will be more. So the current passing through this will become 3 times of the current passing through the other one. So automatically, the increase in resistance lead to a decrease in current through the larger segment, or vice versa. So the magnetic field will be larger because of the more current. Here the magnetic field will be larger because of 3 by 4th of the segment, but the current will be less. So increase in current lead to decrease in strength of magnetic field. Increase in resistance lead to decrease in current, the magnetic field decreases, but there's a large length of the wire to compensate that. Here decrease in resistance lead to increase in current. Even though segment is less, the current will be more and it will contribute magnetic field more to compensate the decrease in the segment of the circle. So final conclusion, the net magnetic field will be 0 at the center, whether it is a 180 degree arc or 90 degree and a 270 degree arc, or any way you divide the circle into two pieces. If it's a uniform resistance pair, the net magnetic will be 0 because they to compensate each other by increasing the current or decreasing the current.